All right, I got a race here because turns out I got a lot to tell you. And so if I go a little too fast, it's not because I don't care about you, it's just I got a lot of information to go through. All right, so first, our roadmap. We're now in full production of Blackwell. Computer companies all over the world are ramping these incredible machines at scale. And I'm just so pleased and so grateful that all of you worked hard on transitioning into this new architecture. And now, in the second half of this year, we'll easily transition into the upgrade. So we have the Blackwell Ultra NVLink 72. It's 1.5 times more FLOPS. It's got a new instruction for attention. It's 1.5 times more memory. All that memory is useful for things like KV cache. It's 2 times more bandwidth, okay, for networking bandwidth. And so now that we have the same architecture, we'll just kind of gracefully glide into that, and that's called Blackwell Ultra, okay? So that's coming second half of this year. Now, there's a reason why this is the only product announcement in any company where everybody's going, yeah, next. Yeah. And in fact, that's exactly the response I was hoping to get. And here's why. Look, we're building AI factories and AI infrastructure. It's going to take years of planning. This isn't like buying a laptop. This isn't discretionary spend. This is spend that we have to go plan on. And so we have to plan on having, of course, the land and the power, and we have to get our CapEx ready, and we get engineering teams, and we have to lay it out a couple, 2-3 years in advance, which is the reason why I show you our roadmap a couple, 2-3 years in advance, so that we don't surprise you in May. Hi, in another month we're going to go to this incredible new system. I'll show you an example in a second. And so we plan this out in multiple years. The next click, 1 year out, is named after an astronomer, and her grandkids are here. Her name is Vera Rubin. She discovered dark matter. Okay, yep. Vera Rubin is incredible because the CPU is new. It's twice the performance of Grace, and more memory, more bandwidth, and yet just a little tiny 50-watt CPU is really quite incredible. Okay, and Rubin, brand new GPU, CX9, brand new networking SmartNIC, NVLink 6, brand new NVLink, brand new memories, HBM4. Basically, everything is brand new except for the chassis. And this way, we could take a whole lot of risk in one direction and not risk a whole bunch of other things related to the infrastructure. And so Vera Rubin, NVLink 144, is the second half of next year. Now, one of the things that I made a mistake on, and so I just need you to make this pivot. We're going to do this one time. Blackwell is really 2 GPUs in one Blackwell chip. We call that one chip a GPU, and that was wrong. And the reason for that is it screws up all the NVLink nomenclature and things like that. So going forward, without going back to Blackwell to fix it, going forward, when I say NVLink 144, it just means that it's connected to 144 GPUs. And each one of those GPUs is a GPU die, and it could be assembled in some package. How it's assembled could change from time to time, okay? And so each GPU die is a GPU. Each NVLink is connected to the GPU. And so Vera Rubin NVLink 144. And then this now sets the stage for the second half of the year, the following year, we call Rubin Ultra. Okay, so Vera Rubin Ultra. I know. This where you go, all right, so this is Vera Rubin Ultra, second half of 27. It's NVLink 576, extreme scale up. Each rack is 600 kilowatts, 2.5 million parts, okay? And obviously a whole lot of GPUs. And everything is X factor more. So 14 times more more flops, 15 exaflops. Instead of one exaflop, as I mentioned earlier, is now 15 exaflops, scaled up exaflops, okay? And it's 4.6 petabytes, so 4,600 terabytes per second scale up bandwidth. I don't mean aggregate, I mean scale up bandwidth. And of course, a brand new NVLink switch and CX9, okay? And so notice 16 sites, 4 GPUs in one package, extremely large NVLink. Now just put that in perspective. This is what it looks like, okay? Now this is going to be fun. So you are just literally ramping up Grace Blackwell at the moment, and I don't mean to make it look like a laptop, but here we go. Okay, so this is what Grace Blackwell looks like, and this is what Rubin looks like. ISO dimension. And so this is another way of saying, before you scale out, you have to scale up. Does that make sense? Before you scale out, you scale up. And then after that, you scale out with amazing technology that I'll show you in just a second. All right, so first you scale up, and then now that gives you a sense of the pace at which we're moving. This is the amount of scale up flops. This is scale up flops. Hopper is 1x, Blackwell is 68x, Rubin is 900x. Scale up flops. And then if I turn it into essentially your TCO, which is power on top, power per, and the underneath is the area underneath the curve that I was talking to you about, the square underneath the curve, which is basically flops times bandwidth, okay? So the way you think about a very easy gut check on whether your AI factories are making progress is watts divided by those numbers. And you can see that Rubin is going to drive the cost down tremendously. Okay, so that's very quickly NVIDIA's roadmap. Once a year like clock ticks, once a year. Okay, how do we scale up? Well, we were preparing to scale out. That was scale up, was NVLink. Our scale out network is InfiniBand and Spectrum-X. Most were quite surprised that we came into the Ethernet world. And the reason why we decided to do Ethernet is if we could help Ethernet become like InfiniBand, have the qualities of InfiniBand, then the network itself would be a lot easier for everybody to use and manage. And so we decided to invest in Spectrum. We call it Spectrum-X, and we brought to it the properties of congestion control and very low latency and a mountain of software that's part of our computing fabric. And as a result, we made Spectrum-X incredibly high performant. We scaled up the largest single GPU cluster ever as one giant cluster with Spectrum-X, right? And that was Colossus. And so there are many other examples of it. Spectrum-X is unquestionably a huge home run for us. One of the areas that I'm very excited about is Spectrum-X is not just for AI clouds, but Spectrum-X also makes it possible for us to help every enterprise become an AI company. And so, was it last week or the week before, Chuck Robbins and Cisco and NVIDIA announced a partnership for Cisco, the world's largest enterprise networking company, to take Spectrum-X and integrate it into their product line so that they could help the world's enterprises become AI companies. We're at 100,000 with CX7. Now CX8's coming, CX9's coming, and during Rubin's time frame, we would like to scale out the number of GPUs to many hundreds of thousands. Now, the challenge with scaling out GPUs to many hundreds of thousands is the connection of the scale out. This connection on scale up is copper. We should use copper as far as we can, and that's, call it a meter or two. And that's incredibly good connectivity, very high reliability, very good energy efficiency, very low cost. And so we use copper as much as we can on scale up, but on scale out, where the data centers are now the size of the stadium, we're going to need something much long distance running. And that's just where silicon photonics comes in. The challenge of silicon photonics has been that the transceivers consume a lot of energy. To go from electrical to photonic has to go through a SerDes, go through a transceiver and a SerDes, several SerDes. Okay, so first of all, we're announcing NVIDIA's first co-packaged option silicon photonic system. It is the world's first 1.6 terabit per second CPO. It is based on a technology called microring resonator modulator. It is completely built with this incredible process technology at TSMC that we've been working with for some time. And we partnered with just a giant ecosystem of technology providers to invent what I'm about to show you. This is really crazy technology, crazy technology. Now, the reason why we decided to invest in MRM is so that we could prepare ourselves using MRM's incredible density and power, better density and power compared to Mach Zehnder, which is used for telecommunications when you drive from one data center to another data center in telecommunications, or even in the transceivers that we use Mach Zehnder, because the density requirement is not very high until now. And so if you look at these transceivers, this is an example of a transceiver. They did a very good job tangling this up for me. Oh, wow. Thank you. Oh, Mother of God. Okay. This is where you got to turn reasoning on. It's not as easy as you think. These are squirrely little things. All right, so this one right here, this is 30 watts, just so keep you remember, this is 30 watts. And if you buy it in high volume, it's $1,000. This is a plug. On this side is electrical. On this side is optical. Okay, so optics come in through the yellow. You plug this into a switch. It's electrical on this side. There's transceivers, lasers, and it's a technology called Mach Zehnder, and incredible. And so we use this to go from the GPU to the switch to the next switch, and then the next switch down, and the next switch down to the GPU, for example. And so each one of these, if we had 100,000 GPUs, we would have 100,000 of this side, and then another, 100,000, which connects the switch to the switch, and then on the other side, I'll attribute that to the other NIC. If we had 250,000, we'll add another layer of switches, and so each GPU, every GPU, 250,000, every GPU would have 6 transceivers. Every GPU would have 6 of these plugs, and these 6 plugs would add 180 watts per GPU, 180 watts per GPU, and $6,000 per GPU, okay? And so the question is, how do we scale up now to millions of GPUs? Because if we had 1 million GPUs, multiplied by 6, right, it would be 6 million transceivers times 30 watts, 180 megawatts of transceivers. They didn't do any math, they just moved signals around. And so the question is, how could we afford, and as I mentioned earlier, energy is our most important commodity. Everything is related ultimately to energy. So this is going to limit our revenues, our customers' revenues, by subtracting out 180 megawatts of power. And so this is the amazing thing that we did. We invented the world's first MRM micromirror, and this is what it looks like. There's a little waveguide. You see that on that waveguide goes to a ring. That ring resonates, and it controls the amount of reflectivity of the waveguide as it goes around, and limits and modulates the energy, the amount of light that goes through. and it shuts it off by absorbing it or pass it on. Okay, it turns the light, this direct continuous laser beam, into ones and zeros. And that's the miracle. And that technology is then, that photonic IC is stacked with the electronic IC, which is then stacked with a whole bunch of micro lenses, which is stacked with this thing called fiber array. These things are all manufactured using this technology at TSMC called, they call it COUPE, and packaged using a 3D CoWoS technology, working with all of these technology providers, a whole bunch of them, the names I just showed you earlier, and it turns it into this incredible machine. So let's take a look at the video of it.